So first off, please get coffee, tea, whatever you need to stay awake through this. And, uh, and right from the start, no, all of the 5 modules today, really the slides are perhaps not the most important thing. The important thing is to generate questions from you that I can then direct to people who can actually give good answers to. Not going to pretend to be the expert here at all, but really just introduce you to the topic. And it's a sort of a soft start, history, and we sort of go towards the end where there's some maths for those of you who want to stick it out for that long. As Tumi says, I used to work for SKA. I still do some sort of consulting for SKA. I still have a university position, emeritus position as well. But my main job is with the SKA, where I'm what's called a system scientist, which is basically a job title where they're not quite sure what to call you. So they think that system and scientist put together sounds impressive. So that's where I am. But let's get into the history, and we'll go right back in history. This is going to be a history of radio astronomy, very, very brief history of radio astronomy, but also a history of radio astronomy in South Africa. And I think one of the things that a lot of people don't fully appreciate is that they see the SKA now and MeerKAT just before that and thinking this was something that just appeared out of nowhere. And it didn't. Now, hopefully I'll show you that South Africa has a long history in radio astronomy. But before you can do radio astronomy, you need radio. And radio astronomy is necessarily a young science because radio has not been around for that long. It was only predicted by Maxwell and others in about 1861. Now, other sciences, physics went further back than that. And then it took a few more years till 1887 before Hertz actually discovered radio waves, that there were these electromagnetic waves. And then quite another sort of decade or so before radio became a thing. And Marconi is kind of, is given, the title of being the father of radio. He started using radio and exploiting it. But the beginning of radio astronomy itself was a serendipitous thing. So now, humans had radio, they wanted to start using it. And one of the first things that they wanted to do was to send radio signals, messages, across the Atlantic Ocean between the UK, Europe, and the US. And when they started doing these first experiments and first installations, they realized that there was a background interference, what was called static back in the day, hiss, that sort of came and went. And Bell Labs was established at that stage to sort of push radio. And they said, they gave Carl Jansky, who worked for Bell Labs, they gave him the job of saying, hunt this thing down, find out where it's coming from, and we'll kill it. So he built this famous antenna at Holmdel in New Jersey at the Bell Labs campus. And he swung, it was a directional antenna, and he swung it around the sky. And he realized that it was coming from a point in the celestial sky. It was not rotating on a normal solar day. It was rotating on a sidereal day. It was fixed to the stars. It wasn't fixed to the sun. And this was now, he very cleverly said, okay, well, this must be coming from somewhere in the cosmos. And he tied it down to the Milky Way. And you can see on his blackboard there, he's pointing out that he's got the constellations in the sky, and there's the Milky Way, and he said it's coming from the Milky Way. Bell Labs lost interest. They said, okay, well, there's nothing we can do about that, and they pulled him off the project. That was it. So radio astronomy was discovered, but didn't go any further at that point. But then during the Second World War, Grote Reber was an engineer in the US, and he'd read Jansky's paper, and he said, well, I want to follow up on this. And he built a dish antenna in his mother's backyard, quite literally. And he went about mapping the sky. And it was back in the day, I mean, you had chart recorders to record your data, and you see what these chart recordings looked like. You see humps. And it turns out that those humps were, as he scanned his antenna through the Milky Way, and then the RFI team will understand exactly what the spiky things are. Those are, this was in the middle of a town, and those are motor cars. So those are all spark ignition cars that are, and so he was the first radio astronomer, and he had to excise RFI from his data. And when he analyzed his data, he was able to make contour maps of the radio waves, the intensity in the sky. And you can recognize immediately from there that there's this band of emission across the sky. And it was aligned with the Milky Way. And he said, well, that's conclusive. No, this stuff is coming from the Milky, no, from radio is coming from the Milky Way. And so he tried to publish the data. And he couldn't. They said, no, it can't be. And because at that stage, remember, this is now, pre-satellites, pre-everything else, everything we knew about the sky, about astronomy, was optical. It was the only thing we knew about. We only knew about stars and galaxies, nothing else. And we'll show later that their prediction was that stars are not going to produce enough radio waves to predict this kind of emission. So we don't have the physics, and so therefore it can't exist. And they refused to publish the paper. Eventually, he got a note in the APJ. But this is the first radio astronomy paper, and it was a big change for astronomy because suddenly there was the signal that people didn't understand. So that's what the sky looked like, according to optical astronomers. Ancient picture, I'll find a better one of these, but you can see the Milky Way in the optical. And if you go and spend 15 years of your life doing a PhD at Hartebeesthoek, you then produce a radio map of the sky, so that was basically how I started my career in radio astronomy, was mapping the sky, basically doing what Jansky did, what Rieber did, but with a bigger telescope and at higher frequencies. And you can see that indeed, yes, the radio sky is dominated by radio waves coming from the Milky Way. And we know that needed to be explained. But the good thing is you learn a hell of a lot more about what the universe is doing. Step forward a few decades, and of course you take MeerKAT, the most powerful radio telescope in the world, and you point that at the center of the Milky Way, and you get these fantastic radio images, which arguably look a lot better than what the sky looks like even on a good dark night with stars. And you see all sorts of things. So radio astronomy has come a long way in its fairly short history. Wars are terrible, but the one thing they do is they develop technology. And in the Second World War in particular, the radar was a big thing. And especially in the UK and to a lesser extent perhaps in other countries, there was a great development of radar for defense systems. And that drove the technology of radio very, very hard. And one of the people in particular who was involved in this radar development was Sir Bernard Lovell. And he worked on airborne radar. So that meant sort of making things smaller, making things more sensitive, and understanding the systems really, really well. And these radar were deployed especially for bombing raids on Germany towards the end of the war. Lovell wrote a book on this called The Echoes of War, and which I've not read, but I should actually, I suppose. But there's Bernard Lovell in front of what he then did after the war. He took those technologies that he developed in radar, and he built what was then and still is one of the biggest radio telescopes in the world, the Mark I telescope at Jodrell Bank, and subsequently the Mark II. He went way over budget. He nearly went to jail because of that he'd overspent basically government money. But he was saved by Sputnik because the Mark I telescope was the only instrument in the world which could track the launch vehicle of the Sputnik satellite. And so he was saved, and that was a good news story. But the Jodrell Bank, the telescope still standing there, and is still a wonderful thing to see. This is a very spotty history, but this sort of picks up a couple of events. Then in 1965, back at Bell Labs, back at Holmdel, where Jansky discovered radio waves, radio communications had moved on to another level. And it was before real satellites, but what was happening is that they were launching big balloons into orbit and then bouncing radio waves off of the balloons to do transatlantic radio emissions. And again, they saw that there was a background hiss. There was a background signal that was annoying, with the attempts at doing these balloon experiments. And Penzias and Wilson, at this stage, were working at Bell Labs. They built this horn antenna, a massive thing, to go and hunt down, just like Jansky, hunt down this interfering signal, and then we can bomb it and get rid of it. So it's not going to because I suspect there was thinkings that the Russians were doing something to interfere with these emissions. But the signal wouldn't go away, and they said, this looks like it's a signal that's coming from the cosmos all over the sky, and it has a characteristic temperature of about 3 Kelvin. And people sort of scratched their heads and wondered what this could be. But again, Bell Labs said, well, no interest to us because we can't do anything about it. We just have to live with it. And so they shut down the experiment. But fortunately, some theoreticians were ahead of the game, and they were saying that if the universe started with what became called the Big Bang, then the universe would have cooled down by now, and it would be at around about 3 Kelvin. And so you would expect to see this emission. So by serendipity, they discovered this signal. They got put in touch with the theoreticians got put in touch with them, and they jointly got Nobel Prizes for discovering the cosmic microwave background. But the interesting thing here that I think it's a sort of an ironic thing, that both discoveries, both the discovery of radio astronomy and the discovery of the cosmic microwave background, where communications engineers were looking for a source of interference, and it turned out to be radio astronomy. Of course, the RFI people in the room today understand that this is completely the inverse of what we have now, where in radio astronomy, we're struggling with the communications people because they're our source of RFI. I think it's one of the great ironies, and I think we should remind the telecommunications people what they owe us. Again, just picking out a spot in the history, because this is very relevant to where we are now with MeerKAT and the SKA, is the invention of interferometry, or aperture synthesis, as it was called then. And the person who was really responsible for this was Ryle, Martin Ryle at Cambridge. He built the real interferometers, and guess what? He got Nobel Prize for that as well. But this was a big step forward in radio astronomy, in the telescopes of radio astronomy. Rather than just having a single receptor, you had multiple receptors, you tied them together, and it gave you the power of an array where you get much more sensitivity and much more resolution. So that's as far as I'm really going to go with the history of radio astronomy globally. I mean, obviously, big telescopes were built all over the world. The Bonn 100-meter telescope, Arecibo telescope, and radio astronomy blossomed because it just opened up this whole new field. But let's take a step back to South Africa and see where we were here. Now, somebody you may or may not heard of is Basil Schonland, Sir Basil Schonland, with various letters after his name. And the OMG is an important one because that links him really back to South Africa. That's the Order of Mapungubwe. Bernie Vanroff has one as well. It was awarded posthumously, obviously. But I must admit to being a bit parochial here because Basil Schonland came from Rhodes University. His father was one of the founders of Rhodes University. But importantly, so there's a book on Schonland called Scientist and Soldier. He was really an impressive person and a great scientist. And he went after from Rhodes, he went to Cambridge, and he worked during the war on radar with Lovell and others. And after the Second World War, the then president, or the then Prime Minister, Jan Smuts, recalled him to South Africa and said, we need to set up a scientific infrastructure in South Africa, and we're going to call it the CSIR. And so he was the person who set up the CSIR here in South Africa. He went back to the UK afterwards. But the book on Schonland was written, his biography was written by a guy called Brian Austin. He got hold of it, and after I gave this talk at the IOU General Assembly, Brian Austin got hold of me because he took issue with what I said about Schonland, as we'll see later. But he communicated with Bernard Lovell and said, "No, can you tell me about Schonland during the war?" And there's this excerpt here that said, actually it's just chopped off at the bottom there now. During the war, they also realized that these new radars that they were developing, there was a source of interference. And of course, the obvious source of interference would have been the Germans jamming the radar. And there was an incident where these two German battleships were able to sail through the channel undetected, which was a huge problem. No, it was obviously a big problem. I mean, but it turned out it was the sun. And Schonland was given the task of finding out where this excess emission was coming from, and it turned out to be radio waves from the sun that were doing it. Sorry, this is a very parochial bit here now, but when I was doing sort of searches for this kind of talk a few years ago, I found on the web there was a newsletter from Rhodes University, and there was an article in that newsletter, and there was the newsletter in 1959, so quite a while ago. I'd just been born, and none of you had. And it was a newsletter article about my department, my physics department at Rhodes, written by Jack Gledhill. And he said, he gave a kind of a potted history of things, and he said, in 1938, the graduates were a guy called Frank Hewitt and Gledhill himself. Now, those are two people who will come up later, so that's why they appear here. There's Hewitt on the left and Gledhill on the right. And Gledhill was professor when I came to Rhodes, a younger version of me. And going on in the newsletter, it said there was this guy called Pat O'Brien. Pat O'Brien was the first person to write a real MSc at Rhodes. We'll see, though, and then so why do I bring him up? Because after being at Rhodes, Pat O'Brien then went to Cambridge, around about the time where Ryle was inventing radio interferometry. Pat O'Brien was the first person to make interferometric observations of the sun. A South African from Rhodes University, little town in end of the world, was the first person to actually use the interferometer to any effect. So when I say that there was a South African history in radio astronomy, it's a real one. There were other people. This guy called Stack Forsyth appeared at Rhodes University. He was a lecturer for a while, and he'd met Pat O'Brien. Pat O'Brien came back from Cambridge and went to what is now UKZN, and Stack Forsyth was there. O'Brien told Stack Forsyth, who was an engineer, about radio astronomy. Stack Forsyth then got a job at Rhodes, came to Rhodes, and he said, oh, I want to get into this, and built the first radio telescope in South Africa in 1958. This was on the university campus. It was a helical antenna stuck on top of a shack like this. So radio astronomy in South Africa goes back to 1958, which happens to be when I was born. The first MSc student doing radio astronomy was a guy called William Shooter. Bill Shooter went from Rhodes to Manchester, and he did his PhD there with Rod Davies, a very famous radio astronomer, and then went to Canada and became one of the preeminent radio astronomers in Canada. And all of the Canadian radio astronomers, more senior radio astronomers that I've met over the years, all knew Bill Shooter. They'd all been lectured by him and didn't realize he was South African. So the shack, as it was called, ran sort of around about 1958 to 1960. The picture on the bottom right there shows where it is now, where it used to be on the campus. These days, it's right in the middle of the campus. There's university residence on the one side, the zoology department, and a lecture theatre all surrounding it. But I still want to get a little plaque put up there. But I mean, these were very primitive devices. It was all valves and put together by students. But a bunch of students went through that program. Pat Wild also went to Manchester to do a PhD, came back to UCT, was a lecturer in the astronomy department here. Graham Poole went to Sheffield and got into meteor physics, radio meteor physics, building radars to look at meteors, came back to Grahamstown and ran a meteor radar. Gerrit Verschuur went to Manchester, got a PhD at Manchester, and then went on to the NRAO and on to Arecibo. But in the meantime, wrote books as well. He wrote a book called The Invisible Universe, which some of you may have read. And he also co-authored a book, The Galactic and Extragalactic Radio Astronomy, with Ken Kellerman. Ken Kellerman is one of the preeminent radio astronomers in the world. So a South African and American wrote a book that nearly everybody in radio astronomy has read, not realizing that one of the co-editors is a South African. And Gerard Diaga also went to Manchester. He built the first digital correlator at Manchester. A South African built the first digital correlator at Jodrell Bank. Came back to South Africa. He was my PhD and my MSc supervisor. Then he came to UCT, and some of you UCT people might remember Gerard from the Lek Eng department there. But going back to Rhodes, Gledhill got involved in, he was an honospheric physicist, but then he thought, let me think about the magnetosphere of Jupiter, And he predicted that Jupiter would have a big spinning disk magnetosphere, which would emit radio waves in the letter to Nature. And that was followed up by my great mentor and PhD supervisor at Rhodes, Eddie Barth, who actually started doing experiments to investigate the emissions from Jupiter. So that first radio telescope at Rhodes was a solar radio telescope. It was looking at solar emissions. Now the radio telescopes moved on to looking at Jupiter. And it still was very, very primitive equipment. Because of RFI reasons, they moved off of the campus. They moved out to outside Grahamstown, now Makanda, and they used Army surplus radio receivers, no valves. And if you zoom in on this one, you can see, in fact, it came from the CSIR. They got the equipment from the CSR, but this was the real pioneering days in the 1960s. So the radio telescope sites now moved from the town into the surrounding countryside largely to avoid radio interference. But there's some fairly modern things now. The TART telescope is on one of these sites. Now I'm going to mention some sort of names which were really central to why you're sitting in the audience here today. So Dirk Baker did his MSc at Rhodes, and he built a whole farm of antennas out on a farm called Craigdoon outside Grahamstown. And he built a radio telescope. When I say he built a radio telescope, from the antennas all the way through to the data analysis. And you can see it was the construction of a swept frequency polarimeter for observing decametric radiation from Jupiter. So it was a polarimeter and a spectrum analyzer. I mean, it was the whole deal. He then went to do his PhD in the US at OSU with John Krause. Now, hopefully some of you know John Krause. You must have read his book. John Krause wrote the textbook on radio astronomy. I mean, it's just called Radio Astronomy. If you haven't read it, you should. It's got everything that you need to know about radio astronomy. It was written a long time ago. John Krause heard about Dirk and told him that he was going to come and do a PhD with him, paid the whole deal. And no, he worked with with that person. He came back to Rhodes, lecture for a while, went on to the CSR, got involved in commercial aspects of antennas. One of the world's greatest antenna engineers, and we'll see more about him a bit later. Then there was a guy called Pete Harvey who did just honors at Rhodes. Then went to Jodrell Bank, did a PhD, and he built the first digital correlator that was used for what was to become the Merlin interferometer in the UK. So a South African built the correlator for Merlin. Mike Ings, tragically, Mike died 2 weeks ago. But he built the first radio interferometer in South Africa for looking at Jupiter. And again, he went into the commercial world, went to UCT, and we'll see he pops up later in our story. Then at Rhodes, we went up in frequency, built a little dish. This was just before I came to Rhodes. The person who was very key in this was a guy called Mike Gaylord, who then went on to Hartebeesthoek. So this is...
Let's interrupt. We've got a hand online.
Oh.
Do you want to take questions as you go, or should we wait?
Yeah, can do.
Okay, Howard?
Justin, just to say, you don't see your audience. I don't know who's with you, but just to say this is a fascinating account, and we're all enjoying it greatly here in Stellenbosch from those of us listening in. But as far as Dirk Baker's concerned, just another little add-on, and that when Cavendish were looking at the bow tie antenna with alloy, and they were trying to get bandwidth, there were all sorts of level problems. It was Jonas Klitter and Justin Jonas, Dirk Baker who suggested looking at LPDA for good or bad. And it was Dirk that allowed us to go to Paardefontein to make measurements of the LPDA, which now forms the basis of many of the antennas out there. So wonderful connectedness. And just to say, it's fun to listen to you. There is a remote audience listening into what you're saying.
Yeah, thanks, Howard. Yeah. But yeah, so radio astronomy was continued at Rhodes with this 22 gigahertz telescope looking for water vapor. But also in parallel at Wits, there were two people who did degrees in Wits. They went on to Cambridge to go and work in Ryle's group. One was Tony Reedhead. Tony Reedhead then went on to Caltech. Tony Reedhead was one of the inventors of self-calibration. So the reason that we get these very pretty images out of MeerKAT. And so again, the South African going there. And then Bernie, who went and worked with Ryle. Well, and and published this famous paper where they classified the Van Roff and Riley galaxies. Actually, I meant to update this. I don't know how many citations there are today, but there's an average of 100 citations a year still for that paper. Back to Frank Hewitt. So Frank Hewitt, this guy who did was at Rhodes, his degree at Rhodes, the same time as Gledhill. Schonland employed him to form what became the National Institute for Telecommunications Research at the CSIR. And he was instrumental. No, so when Schonland came back to South Africa, he'd learned about radio astronomy. He knew Lovell and everything else. He said, but when South Africa's never going to do radio astronomy, it's way too expensive, and the Australians have got ahead of us because the Australians took all that technology as well and they started developing. So he said, not going to happen. Hewitt didn't like that. Hewitt went behind his back and went to the US and went to NASA and said, come and build a satellite tracking station in South Africa, which they did. They needed a zero longitude station. And so Hartebeesthoek was built. George Nicholson worked at Hartebeesthoek. He was and he had an interest in radio astronomy, and he used the telescope to make a map of the Milky Way, as we do, and which complemented a map that had been done in the northern hemisphere by a similar NASA dish. NASA allowed host countries to use the instrumentation to do their own experiments. George is the real hero of radio astronomy in South Africa. He then worked with Australian colleagues to do the first VLBI, intercontinental VLBI in the Southern Hemisphere, using the Hartebeesthoek station and two stations a station in Australia and Goldstone in California. So there were 3 NASA stations. They did the very, very first VLBI experiments. Also got the first VLBI fringes ever with the 100-meter telescope in Bonn. And sort of that has no repercussions now, where we're also doing with MeerKAT, trying to do VLBI with the 100-meter. And then Hartebeesthoek became really the central node of VLBI in the world because of where it is. If you're going to do VLBI, you need Hartebeesthoek, or you need South Africa in your VLBI station list, because we can talk to everybody in the world except for Hawaii. NASA withdrew from South Africa, left the dish behind. And it was a sort of a sudden decision that was made, and the announcement was made in the Rand Daily Mail. Ironically, the only issue of the Rand Daily Mail that's not on their archive is that issue that announces NASA's withdrawal. But Hewitt said, don't worry, we are going to use that dish for radio astronomy purposes. He put that in the newspaper, and as George says, well, that changed his life, and it certainly changed my life. So Hartebeesthoek was established as a radio observatory. Some pictures from the days. Peter Harvey, who had built the correlator at George Bank, came to South Africa, designed a correlator, autocorrelator for spectral line work at Hartebeesthoek. We took over the station, with that era technology. The thing there with what looked like mag tapes, those actually paper tapes. That's the APP, the antenna position programmer. Each of those little cards that are plugged in there is a little circuit, a transistor logic, so a flip-flop or an AND gate or whatever. But it was, unfortunately, it's chopped off at the bottom there, but it was wonderful for drying clothes because it would just blow this hot air out the front, this hot air, cold aisle story. And these were when I first started going there. Rhodes, basically Rhodes gave up its own sort of exploits in Grahamstown and threw its lot in with Hartebeesthoek. We got 20% observing time for that, and we, and that was the basis of a whole lot of students getting their degrees. Sarah Buchner being one of them, and me. And it's their 50th anniversary this year. So there's the control room back in the day, sort of ancient computers. Well, they were new computers back then. But to be a radio astronomer back then, you still had to be the complete radio astronomer. You had to know the system from front to back, and because you were just left on your own. And we observed at night, and you had to stay awake all night to watch the thing working. So it was the era still of the complete radio astronomer. Just again, very sorry about the parochialism of this, but it does turn out that Rhodes was a very big player in radio astronomy back then. This is the class of radio astronomy, the physics department in 1980. And I've picked out some people in there. Pete Mountford did the control system for the Hartebeesthoek telescope. Myself, Claire Flanagan, the first pulsar astronomer in South Africa. did a PhD on the Vela pulsar, had a single author Nature paper. Andy Graebe is now Andy Gutz. Those of you who are working on SKA software will know about Tango. Andy is the architect of Tango. George Gruber, less said about him, the better. He was supposedly a radio astronomer. Graham Poole was the meteor person. Jack Leadhill was Jupiter. Eddie was Jupiter and later on radio astronomy. Gerard, person who built the first digital correlator at Jodrell Bank. And Graham Obram, who taught me about control systems and did the control system for the Rhodes telescope. So no, you can see that in 1980, there was a good smattering of radio astronomers around. Hartebeesthoek has gone on to do great things and is now basically the center for geodesy and astrometry in Africa. Later on, we developed Hartebeesthoek, upgraded its surface. It was designed to work at 960 megahertz. It now works at 22 gigahertz. That meant replacing the surface with a solid surface, two upgrades of the surface, upgrading the control software. The control software, Andy Gotts came across to South Africa for a year's sabbatical and used the software that he used at ESRF in France to control that, to control the Hartebeesthoek telescope, and we called it TACO, a telescope and accelerator control object. And you can see it's not a big step from TACO to Tango. That was the beginnings of Tango. So the control system for the SKA telescope is based on the control system that's at Hartebeesthoek. Hartebeesthoek had a bunch of directors over the years. George was the founding director. He had Roy Booth, who was a very prominent radio astronomer from Europe, came out. Mike ran the place for a while, and I ran the place for a while as well. Big step forward. The SKA happened. I'm not going to go into the history of the SKA. There was the SKA. Starting in about 1990, in 2000, Rob Adam said, and Khotso Mkheli, who was the CEO of the NRF back then, said we need a new big radio astronomy. We need a new big astronomy project. We're just starting to build the SALT telescope. We need something to follow that on. Won't go into the process here, but what happened was we said, okay, let's think about this SKA thing. Let's get involved in the SKA. A steering committee was put together, and these are the key people from that steering committee, but later in life. So Bernie Vanroff, Rob Adam, Khotso Mkheli, George Nicholson, and myself. And we set about getting involved. In 2001 was when we first got involved. I was dispatched to what was called the ISSC, the International SKA Steering Committee. And you can see I looked like a deer in the headlights, kind of just standing there. I was absolutely out of my league completely. Interestingly, in this picture, just sneaking behind me over there is Peter Wilkinson, one of the founders of the idea of the SKA, and Peter Dewdney, who is the architect of the SKA. Anyway, that was beginning of interesting things. A few years later, I went to this is my very first PowerPoint presentation I gave to Cabinet to say that South Africa should get involved in the SKA. Rob was there, and Bernie was there supporting me, and we sold the idea, and the government said, yes, let's do this. In quick succession then, South Africa became a full member of the SKA. As it was back then, there was no money involved. It was just a sort of a talk shop, and we hosted here in Cape Town at the Botanical Gardens. We hosted the committee. Round this table here, there's Phil Diamond, the big boss, today. But we needed a site, and so I was dispatched to go around the Karoo and the Kalahari and the Makua to go and find a site. It was a bad time to be my student, because I would say on a Friday afternoon, what are you doing this weekend? And before the student could answer, I would say, you're coming with me. Pack a sleeping bag, and off we would go. And we would do the first RFI measurements to go looking for a good site. We went out with ICASA. ICASA, we had a very good relationship with ICASA. We used their equipment at the time and my students, and off we went. We found the site. We protected it with an act of government. And then we bid for the site. It was an international bid for the site. There were 2 rounds. There was a knockout round, effectively, and then a final round. And there were 2 bid teams. And there was a common between those teams, and there's some people still around today. Those of you who are HCD students will know Sangeeta. She was around right from the start. You'll certainly know Kim if you're an HCD student. You'll know Adrian, and hopefully you'll know me. So no, there's still some of us around from those days. First bid was in 2005, the next one in 2011. And as everybody knows, well, we won't get there. But we also had a technical team. And again, what did I do? I went to the people I knew from Rhodes. Mike Ings, Dirk Baker, myself, Mike Gaylard, George Nicholson wasn't from Rhodes, but we gave him an honorary degree. Paul Manners was my student. Adrian was my student back then. And Alex was actually a geographer, but we needed a GIS specialist. That was the technical team that we started with. That was it. That was in the Rosebank office. And we put in the bid documents, and we did what we had to do. It's a huge amount of work. And South Africa was the preferred site. It was one of the weirdest days in my life when that announcement came out. The picture at the bottom right there is me rewriting the minister's speech just before she gave it, because she realized that it had the wrong spin. Then we said, okay, we're going to build telescopes. We're not just going to be part of the SKA. We're going to have to build something. And so we put together an engineering team. And there again, you'll see names: Mike Ings, Jasper Horrell, Sibisiso, Thomas Kissel, Adrian, Alan Langman, myself. Not surprisingly, most of these people were Mike Ings' students. And you can see on the desk over here, we actually have Krause's book on radio astronomy, which led us. We went to the international science community and said, if we build a big telescope before the SKA, what do you want us to do? What's the science that you want us to do? We put out a call for proposals. We got the proposals back, and those are the KSPs which we're still running on MeerKAT today. Some of them have now finished, but some of them continue. And actually, that's my boss, sitting there. He was on the selection panel for the science programs. The rest of the world came to the party. They really helped us. We went to all of the observatories around the world, and they all supported us and gave us an immense amount of technical and moral support. We built prototypes for what was to become MeerKAT, the XDM at Hartebeesthoek, Cat 7, still standing there today. We went into big infrastructure builds, and we built MeerKAT. We inaugurated MeerKAT. The SKA grew up, became a real organization. There was inauguration of the first dish, SKA dish, and commencement of, well, the commencement of the construction on the SKA. But just to finish, the big success has not just been that we've been building stuff. We now have hundreds of radio astronomers in South Africa. And I sort of played up the past where I said there were always people doing radio astronomy in South Africa, but it was very, very small numbers. It was certainly male and white dominated. Today, that is not the case. Today, we have a very diverse, very large group of people in South Africa who are radio astronomers, either on the engineering side or the science side, or bridging both of those. And so that's where I'd like to end here. And I think there's quite a lot of you here who belong to that group. Oh. Anybody out there still? Can they hear me? Okay.
We're all out here, Justin. We're enjoying it.
Okay, cool. Thanks. Yeah, so that's a brief history of radio astronomy, mostly in South Africa. So thanks very much for lasting the first round. And I'm very happy to take questions.
Okay, that's a thumbs up online. I'm guessing that's for the audio. Do we have any questions in the house? I'll start with Christo. Just raise your hand and I'll bring the mic.
Hi, Justin. Thanks for this very cool tour for history. I have an interesting question that came up at the BRI a few months ago. Now, I was with a former colleague of my wife's. Her contractor husband asked me, what is the point of all of this? Now, I could explain to him what the point of MeerKAT is and building engineering, but he didn't ask, but okay, he sees that. But what is the point of radio astronomy for, I would almost like to say, normal people?
Yeah.
Because I couldn't get to that answer very quickly.
No, it's a question that all scientists should actually have a very quick elevator pitch answer for, and we should. But it is difficult. But I think there's a few different ways of looking at this. When we started the project, when Rob Adam first initiated the project, we used the term mission-driven innovation. South Africa was really good in mission-driven innovation. The problem was that our missions were things like war. and supporting apartheid and those sorts of things. And like the Second World War, though unfortunately it's mostly been conflict, but this was an opportunity to use a completely benign thing, astronomy, to drive innovation. And so on the engineering side, we do push cool engineering things. I mean, no, we really do. I think we provide a good environment for development of tech. But a more sort of social aspect to it is, and especially being in the African context, it's absolutely essential, I think, that modern cultures should include science as a big thing. That really, and I think there's a feeling both internally and externally that science is not part of African culture, which is just rubbish. I mean, we've proved this. And, I think that's a really important thing, that, it's a cultural thing, that we, South Africans and Africans can be scientists. They can be world-leading scientists. I was speaking to Angus Patterson this weekend. Angus, if you don't know Angus, he's Ponso's boss. He and I are long friends. And we were discussing, this whole thing. And he's a biologist. Now, there's always been a strong thing, science sort of around biology in Africa, because we have the animals and we have the plants. So that's why, and generally people have come here and have appropriated that. Astronomy, MeerKAT in particular, okay, we've got the southern sky, but we built MeerKAT. Africans built MeerKAT, and the rest of the world are coming here to use our instrument. That's a huge turnaround. I mean, I think we're sort of boiled in it, and so we don't really think about it so much. This is a big difference. South Africa has built something itself that other people in the world will leave everything else behind to come and use. And I think that's a very, very strong cultural message, that Africa can do these sorts of things. So yeah, it's not an elevator pitch, but no, that's that. And developing things to look at the stars is arguably much better than developing things to drop bombs on other countries. So not surprisingly, I mean, a lot of you probably in this room have worked in the military industry and have naturally come to SKA because the technologies are the same, but it's a much nicer environment to use them in. Long answer to your short question.
Okay, we don't have any hands online. Another one in the room.
Hello. I work in software, so supportive of the radio astronomy, and actually as an accidental conversation, I figured out that interferometry and optical imaging are not pixel based. Can you give a short description on how interferometry works and differs to sort of capturing images with pixels?
That's lecture 5.
Okay.
but no, but it's a good question. So it'll be actually, I'll touch on it a bit in the next lecture, but we don't do direct imaging, generally don't do direct imaging. And the reason is that our wavelengths are very long. So your pixel detector, size of your pixel detector is related to the wavelength of the signal that you're getting. So your digital cameras, the wavelengths are nanometers, and so in a CCD this big, you can get millions of pixels. Our radio wavelengths are this big, so our pixel size, detector size, would be this big. So if you had to build a direct imaging camera, that would be the size of just your pixels. But then your optics are going to have to be much bigger than that. And so if you wanted to build an imaging radio telescope, it would be hundreds of kilometers in diameter. So what we do instead is we place the antennas hundreds of kilometers apart. And the magic of interferometry allows us to say, well, that's the size of our antenna. So, but it's the von Sitter-Zernicke theorem, if you want to know, it's in the last lecture. But it says that if you take two antennas and you correlate the signals between them, then what you get is the Fourier component of the image at that baseline, at that distance. And then if you do a whole lot of those different baselines, you get the Fourier transform of the image, and you take the Fourier transform of that, and then you get the image. So it's indirect imaging. It's used in other areas as well, but that's the basic difference.
Okay. Yeah, it doesn't seem like we have any other questions. I'll ask a question. When you started out your career, if we think about it back to when you were studying, knowing that we didn't have much in terms of astronomy as a career or industry in South Africa, were you looking at it when you decided to go into the field as something that you would do and go work elsewhere? Or did you actually think this is an industry I want to help build within this country?
That's a silly question to ask, to me, because that's got a 2-hour long answer. But there's a paper coming out in a book which you can read. I wanted to be a radio astronomer when I was 13 years old. I wanted to build radio telescopes since I was 13. I'd read about radio astronomy back then. The electronics magazines, Wireless World, that sort of thing, had pictures of Jodrell Bank and the Goonhilly Earth Station. Big dishes. Dishes were just a thing that I wanted to do. At school, one of my teachers had been to Rhodes and he knew about radio astronomy. We had a radio group. We tried to build a solar radio telescope. I went to Rhodes University because they had that 22 gigahertz dish standing outside. They went to Hartebeesthoek. And, it just happened. I mean, I always just wanted to build radio telescopes, and I went on to build the biggest in the world. So, I mean, what kid at 13 can have their dreams come true? I pinch myself every day. I've never made a decision in my life. They've all been made for me. I've never had a job interview, proper job interview. I've never applied for a job. I've always just gone from one job to the other because I said, "Oh, you want to do this? We wanted you to do this." Cosmo Khedi said, "I want you to be director of Hartebeesthoek." Rob said, "I want you to drive the SKA program." And that was it. They were all people you didn't say no to. And so I was, I like to say lucky, but I can't say that I had any it was all decided by others. It wasn't me. My excuse. So if it all goes wrong, it's not my fault.